Okay, everyone, welcome to part C of the Theories of Motor Control lecture. And for this last section of this particular lecture, we're going to speak about the dynamical systems theory. Now, I know you've heard me mention this throughout the last sort of 10 or so weeks, and specifically we looked at this in week 1. But what I'm going to do, I'm going to summarise now. We're up to slide number 19. And so in 19 and 20, I'm going to summarise in the next sort of couple of minutes. So here, according to dynamical system theory, we really look at learning. The first thing we try to remember, it's a non-linear approach to learning, meaning it's dynamic. That learning doesn't necessarily progress in a nice linear fashion. It can be exponential and logarithmic and change really abruptly from one stage to the next. And even going back to those stages of learning, we looked at the cognitive stage and associative stage, and that looks really a nice linear approach. But the change from the cognitive to the associate is very different depending on the task, depending on the person, and depending on the environment it's being performed in. And you can see no change and still be very cognitive. Then suddenly, like that, the next training session, you could get that jump to that next level. And that's really the feeling we're trying to create here in trying to describe how we learn from a dynamical systems theory, because it literally is an abrupt jump from one phase to the next, and it's not necessarily predictable of when it's going to occur, and it can be different from one person to the next, and it can be different from one person when they perform one task compared to another. Meaning one person could pick up a task really easy, if we go back to the abilities in week 1 as well, but another task they might find really hard to do and not pick up as quickly as others. So really what we're trying to describe here is that according to dynamical systems perspective, it's a nonlinear approach. Now secondly, it comes from really chaos theory or ecology, sort of nature and laws of nature. So things like, we describe things like flocks of birds or hurricanes or different systems within nature. And they all sort of happen in a dynamical way. In other words, a hurricane gets created when just sort of the winds at the optimal speed, at the optimal temperature, and suddenly there can be nothing, and then suddenly, boom, a hurricane can come literally out of nowhere, or a tornado can come out of nowhere. And then it can go down a street of houses, and it can destroy all except one, or it can just destroy one, and all the other houses around it are untouched. It's literally that dynamic and that unpredictable. And that's really where a lot of these sort of theories of motor control in relation to dynamical systems theory will sort of come from. And I could go into a lot of where they came from, but for the nature of where we're at for this particular lecture and this degree, this unit, that just tells you pretty much what we're saying of where it comes from. Now, the key here is sort of point number 5 on slide number 19, point number 4. Behavioural changes are not always continuous, linear progressions, but often abrupt and sudden changes. And I think that's the really thing to emphasise, and the system itself self-organises over time. So I'll explain that. We go to slide number 21 now. So 21 now says dynamical pattern theory, concepts, self-organisation. And this is really the key to what actually happens when we learn from a dynamical systems perspective. Over time, with practice, our body self-organises itself to be able to produce the new movement pattern that we're trying to produce with practice. So in an early stage of learning a skill like a tennis serve or a throw or a catch or maybe baseball hitting, whatever it might be, we have all those cognitive issues. We're making a lot of errors, we're very frustrated, it's very cognitive, the movement's very rigid, it's uneconomical, it's not adaptable, it's not persistent, you name it, we're not improving. But then over time, with practice, we start to get those adaptabilities, persistence, we start to become more economical, we start to release our degrees of freedom. But what actually happens is, it's because the muscles that are interacting with the central nervous system over repetitive times of practicing, and they self-organise to produce a new movement pattern, which is, again, more economical, more persistent, adaptable, and that continues to happen in the learning process over time. So this process called self-organisation just means the body interacts with the task itself and the environment to produce a new movement pattern through the process of self-organisation. Okay, and that's slide number 21. So let's go to slide number 22, and you've heard me mention this quite a lot, but especially in the last sort of couple of minutes, is this whole term called constraints. So according to dynamical systems theory, it's what's called a constraints-led approach to learning, meaning it's not necessarily about a motor program that's just embedded in the brain we have to access. Learning and the development of skill or skill ability is a combination of the constraints within the system coming together to produce a movement. So it's what's called a constraints-led approach. And according to these theorists, the constraints on the system are these three things: the organism, so the person, the environment they've got to perform the task in, and the task itself. Alright, so the organism is obviously the person, and here you've got the person's own genetic makeup, their cognitive, psychological, and emotional attributes, all those things go into it. Then you've got the environment, the different conditions it has to be performed in. So let's say, for example, you've got a person that they're learning to do a tennis serve, and they're quite good with hand-eye coordination. So the organism itself, the person could be quite strong, they might have good levers, so very tall, so therefore they might be quite suited, quite athletic, so they're suited towards the tennis serve. The environment might be indoors, so no sort of conditions which impact it, and the task itself is obviously the tennis serve, so that could be one way for them to learn a skill, and they're the three constraints on the system. But then you might have roller skating, and that might be the same person again. This time the organism is a bit different. It's not maybe as suited to the particular task. Being tall and gangly might necessarily be suited to roller skating or ice skating, where it's more the shorter limbed, more I guess sort of ectomorph type mesomorph type body type might be more suited, as opposed to the ectomorph might be more suited to the tennis serve. So what we're trying to say here is that constraints-led approach, meaning it's the constraints on the system itself which dictate the actual movement outcome itself. Okay, so now we're going to slide number 23, and one of the key things we talk about from a dynamical systems perspective is what is called an attractor. So attractor is almost the attractive movement state, if you like. So a stable state of the motor control system that leads to a behaviour according to the preferred coordinative patterns. So a characteristic of an attractor, it's identified by what's called these order parameters, control parameters, and stability and its energy efficiency. So what does that really mean? Alright, so according to dynamical systems theory, there's a couple of different parameters that we look at. So it's very different to motor programs, so don't confuse parameters with motor programs with dynamical systems. Now, according to the definition here, the order parameter is almost the movement itself. So it could be walking, it could be running, it could be catching, it could be throwing. Now, I'm being a bit crass with that definition, but for where we're at now for simplicity, let's just refer to the order parameter almost like the movement itself. The control parameter is the things that influence the order parameter. So if we look at walking, for example, if I was going out walking on the flat, all right, at a normal pace, that would be what the order parameter is. The control parameter would be obviously the level ground and the speed of the movement. If I then change to uphill walking, so I've changed the control parameter because I've actually changed the surface we're walking on, now we're going uphill. That will straight away influence the order parameter. It'll change the movement by making maybe shorter strides, lean forward. It'll change the actual movement itself. Also too, if I got someone to walk faster or slower, that would also change the order parameter or the movement. So this is how I just try to remember it. The order parameter is the movement, and the control parameter, things like speed or terrain, that can influence the order parameter itself. Right, so an attractor is this attractive movement state. So an example might be that if you see sometimes elderly people swimming in the pool, people have been swimming for years, but they're not that good as swimmers, but they can do it for hours on end. It's almost like they throw their arms over, but it looks really inefficient and it looks really uncoordinated, but they can do it for over and over again. So that's actually a very stable movement pattern. That's a strong attractor, but it's not a very good movement state. So if we want to change their movement pattern, we actually want to try to change what they're doing. That's really hard to do. So we want to get them out of this slide here, slide number 23. We want to get them out of the deep attractive basin, a stable state, and get them out of there into that less stable state so we can actually change their movement pattern. And that's really hard to do. So that's why it's so much easier to teach someone a new skill that hasn't done it before, than someone that's already got a strong movement pattern. It's really hard to change. So that slide here just shows you it's why it is harder to teach an old dog new tricks, because they've already got really strong, stable movement patterns that are really hard to change. But that's what an attractor really is. It's a really stable movement pattern. So when we're first learning a skill in that cognitive stage, our movement pattern is very unstable. It's really important that we get good habits early on, so we do a correct movement pattern, because after a while, that new movement pattern will become stable, it will become a more attractive movement pattern, so therefore it'll actually have these characteristics where there'll be minimal child-to-child variability. So this is still in slide number 23, about the fourth point down. So one of the characteristics of an attractive movement state or pattern is this: there's less variability from one child to the next because it's a lot stronger. It's actually more stable, and it's actually more efficient as well from an energy perspective. So that just gives you an idea of what an attractor is and how it might relate to different movement patterns. Okay, slide number 24 is the autoparameter. So I've just explained what the autoparameter is, so we don't have to go through that necessarily again now. Slide 25, the same thing. It's talking about that control parameter, and I've just said there, a variable when increased or decreased will influence the stability and character of the autoparameter. That is what a control parameter is. It's important to identify it since it becomes the variable to manipulate in order to assess the stability of the autoparameter. So what we mean by that is, we want to know how strong or stable a movement pattern is. If we manipulate control parameters, which will infect the autoparameter, almost like a transfer test, that tells us how stable and strong that movement pattern is if they can keep doing it. All right, so that would be an example, like I said, in the walking uphill or walking faster or slower. Now, what I'm going to do is just show you an example of these control and autoparameters from skills done by an experiment done by Kelso back in the 80s. And this is an easy one to be able to follow, and it shows us how the different control parameters can impact the autoparameters. So in this particular experiment, there were two different autoparameters. There was like what we call in phase, right, or anti-phase. So they're the two different movement patterns. So there's this one here, I call them finger wiggling things, and then this movement pattern here. Now what was really interesting in this experiment was they had a metronome, so it literally go beep, 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 and it would tell you the time to go into, faster and slower, beep, 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 beep. Now what they found is, everyone who did the experiment, that as the metronome got faster, they could do that movement, not a problem, beep, 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 so they could do that, right, until it got too fast they couldn't do it, but that's what they did. Now interestingly, everyone that did this one, right, so this is what they call the anti-phase pattern, but you don't need to know that, okay, within phase pattern. So this one here in particular, what they found was, as the metronome got faster, they did this, and then for every single person that did this particular pattern, when it got faster, there was a certain speed where they went into this one. So in other words, they went beep, 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 and as it got faster, automatically without meaning to, they went into this one here. That told us that that control parameter, the speed of the metronome, was the thing that influenced the autoparameter and changed it once it got to a certain speed, and it was different for every single person. So this is one of the first experiments of really strong evidence in human movement to show, I guess, evidence for the dynamical systems theory. So slides 27 and slides 28 are just showing you those in-phase movement patterns and anti-phase movement patterns from the experiment from Kelso. So really, all we're trying to show there is the dynamical systems theory and give an example of that. So if I can just summarise briefly dynamical systems theory, we first of all know it's derived from chaos theory. We know it's definitely non-linear. That's its real crux. It represents changes that abruptly change from one to the next, are non-predictable and non-linear in nature. So we know that. We also know that according to dynamical systems theorists, that one of the big attributes of the particular, theory is that a system will self-organise over time, and it will be led by the different constraints of the system, which are the organism, the person, the environment, and the task itself. So it self-organises in relation to the constraints of the actual system. We then know that there is an attractor, which is that stable movement state. Stable movement pattern that a lot of people are into, and once they're in that, it's really hard to get them out of that. It's really hard to change. And then we also know there's two major components to the dynamical systems theory, and it is a control parameter and an autoparameter. So the autoparameter is the movement itself almost, what's called relative phase, so the movement, whether it be walking or running, and the control parameter is the speed of the movement. So an example in dynamical systems theory, from walking to running, unlike motor programs theory, it just says this, that people are walking on a treadmill, right? And then the control parameter is the speed of the treadmill. there'll become a particular point of speed for everyone that's different for everyone, that they will get to a speed where they'll stop walking and they'll automatically go into a slow jog, into a run, because it's a different transition from one to the other. So in other words, the order parameter, the speed of the treadmill, is changing the control parameter from walking to running. It's going to be different for each person. I might start running at 9 kilometers an hour, you might start at 11, someone else might start at 15, someone else might start at 6. So it's different for every person. So that's just the evidence for dynamical systems theory. Now, I know it's not going to explain the whole thing in 10 or 15 minutes, but for where we're at for this particular unit, and for what's definitely going to be examinable, these three parts, part A, B and C, cover everything that you'll need to know and you'll need to answer in relation to the exam on the theories of motor control. But as you can appreciate, it's really in depth. It comes in a lot more detail and it could take a lot more time to talk about and discuss it. As you know, I think it's fascinating. I think it's a really interesting, point of where people are at. As you can see, I'm a bit biased in the sense of I'm, sold on the dynamical systems theory of learning. Other people, a lot of them a lot smarter than me, are still very much in relation to motor programs theory. The reality is it'll probably be a hybrid of the two. There probably needs to be some hierarchical control or command, some long-term memory sort of attribution as well, and that together with the constraints of that approach and the fact that learning really is a non-linear, aspect, hopefully will probably be a hybrid of the two in future to come. But, thanks for listening. Good luck this week in the lectures and the labs. I'll be away, but you can email me anytime. I'll try to get back to you as soon as I can. And otherwise, we'll see you in week 12. And good luck in your second assessment 2 for 2:30. And sorry I can't be here to join you this week. All right, see you guys.